So it's 2:40. So let's start our second session. Hello, everyone. My name is Jason Cho, session chair for this session. In this session, we have a topic on recent development in high-dimensional data analysis, non-parametric statistics, uncertainty quantification, and machine learning. So I'm unable to have the Zoom official time app on my system, but instead, I will individually message each presenter at a 10-minute mark and 15-minute mark. We are definitely behind on time, so please be mindful of the time. So for our first speaker, we have Jeremy Flood. Jeremy is a PhD student in North Carolina Agricultural and Technical State University, and he will be presenting on survey data integration for cumulative distribution function and quantile estimation. Please welcome Jeremy Flood.
Hi, let me share my screen. All right, is my screen sharing okay?
Yep.
Awesome. I am so excited to be here today to present a little bit about my research entitled Survey Data Integration for Cumulative Distribution Function and Quantile Estimation. And so first, I wanted to kind of talk about the need for data integration. So specifically, before we talk about how we can integrate data sources together, it's important that we talk very briefly about the different types of samples that exist. So in general, we have two different types of samples, one being probability samples. And very generically, these probability samples are generated using some probabilistic design that ensures every single possible sample from some finite population has a strictly positive chance of selection. And when we have access to these, what we call inclusion probabilities that tell us the probability that a finite population element is included in the sample, we're able to use their inverse to control for sampling bias. Unfortunately, these type of samples come with a set of limitations, the biggest one being the fact that they are very expensive. So they're expensive, they're prone to non-response, and unfortunately, because they are so expensive, they generally do not have as much information as we would like them to have. So in recent years, there's been a little bit of a push in literature to consider non-probability samples, sometimes called convenience samples, to complement the missing information in these probabilistic counterparts. Now, these convenience samples get their name because they truly are convenient. They're flexible, they're rich, and they're cheap sources of data. I think a really good example of a convenience sample would be web scraping data, where we're trying to gather as much information as we can from, say, a social media website like Facebook. Now, convenience samples have their own respective costs. The cost of convenience is that we are not sure if a probabilistic design was used to generate the sample. And because we do not have access to this probabilistic design, we have no way to know or control for any potential sampling bias. So the idea of data integration, or its essential spirit, is trying to integrate information from both of these samples, essentially to leverage the strengths of both. So to give a little bit of an example as to when data integration is necessary, one of the most important ones being when we are interested in performing inference towards vulnerable populations. So inference towards vulnerable populations are very difficult because this information is likely to be protected and classified. So you may not be able to access, or you may not be able to gather a new probability sample, but you will likely have access to an old one, say from the Centers for Disease Control and Prevention. But these old ones may not actually contain the information that you are interested in estimating. They may only contain common demographic variables like sex, age, gender. So the idea of data integration in this context is we can take these small probability samples and essentially combine them with a convenience sample that's much larger, essentially, again, to emphasize the strengths of both particular types of samples. Another good idea is in the context of political polls. And we know that usually before a really big election, there are a number of different political polls that are trying to predict the new candidate. Unfortunately, a lot of these polls, if not all of them, are prone to some degree of error. And you don't know the outcome of an election until the election has already happened. So one thing that we can do is that we can access these demographic variables, which we assume to be public knowledge. We can gather our own probability sample, and we can use these political polls essentially to assist us in performing inference as to who will be the next candidate. So in both of these examples, the idea, again, is to take a probability sample that may be rigorous, but it has its own set of limitations, and essentially to emphasize the strengths of these probability samples by integrating or combining information in a non-probability counterpart. So let's talk a little bit more about how the data integration setup is. So for the remainder of the presentation, I will be saying A and B a lot, and A is going to denote a probability sample of size little na from some finite population U of size big N. Now, the interesting thing about this data integration setup is that we're making the assumption that within the probability sample, we have access to fully measured covariates, which we call X1, X2 through XP. And you can think of these covariates essentially as auxiliary information that give us context to the variable that we are interested in, but are not exactly that are not exactly that variable. Whereas B is our convenience sample, which also has that same set of measured covariates, but has access to the variable of interest. So again, we have a probability sample with measured covariates, and we have a convenience sample that has measured covariates and the variable of interest. So the idea of data integration essentially is to use information in B to input the missing information in its probabilistic counterpart. In most cases, we're interested in estimating the finite population mean, but this research takes a little bit of a different direction. So suppose we're interested in estimating distribution functions as well as quantiles. Specifically, in this research paper, I'm interested in estimating the cumulative distribution function, which tells us in the finite population, it tells us the proportional observations in the finite population whose y is at or below a cutoff t. A good example as to when estimating the CDF, a cumulative distribution function, is important is if we're interested in estimating the proportion of individuals in our local food desert who has an income at or below poverty. Now, inversely, we can estimate the quantile to be the smallest point in the finite population for which the CDF at that point is greater than or equal to a percentile. And a good example as to when this is important is if we are interested in estimating, let's say, the 80th percentile of weight after we condition on some demographic variables like age, sex, and race. And so for the remainder of the presentation, I'm trying to answer one very crucial question, which is, how can I estimate the CDF and quantile function using the sampling setup I defined in the previous slide? So we have a little bit of a hurdle because y is missing in our gold standard sample. So we need a way essentially to impute this missing information. So in one way we can do this is by posing a semi-parametric assumption on the distribution of y in the finite population. So we're going to make the assumption that y follows this semi-parametric model. And we know that this is semi-parametric because if I take a look at the conditional expectation of y given x, I think that this conditional expectation is represented by some smooth but known function of x. And I also think that it's parameterized by an unknown vector of coefficients. So the crucial part of the semi-parametric approach is that if I want to impute the missing y, all that I would need to access is an estimate of those coefficients. Let's let beta n denote the estimate of the coefficients in the finite population. So it is our estimate of the true parameters had we had access to the entire finite population. And lastly, we let epsilon denote some random error term such that its first moment is 0 and that its second moment is constant. So again, all that we would need to impute the missing y in our probability sample is an estimate of these coefficients. But y is only measured in our convenience sample. So we need to use our convenience sample essentially to build a model to obtain these estimated coefficients. So specifically, we're going to let beta hat denote a sample-based estimate of beta n, again, where beta n is the estimate of the true parameters had we had access to the entire finite population. Now, beta n is going to be chosen to solve a very generic score function. The reason why it looks a little bit complicated in this case is because we are using the more generic semi-parametric assumption. But if we think about simple linear regression using ordinary least squares, then this estimation procedure reduces to a significant degree. Again, the reason why it has to look a little more complicated in this case is because we are making the more generic assumption of semi-parametric. We're making the more generic semi-parametric assumption. Now, when we have access to those estimates of the coefficients, we are now ready to use them to estimate the finite population CDF. And so in this slide, I'm very briefly describing our residual empirical CDF-based estimate of the finite population CDF. And the idea is, if I build a regression model on our convenience sample, I can use that regression model to obtain residuals. Now, once I have access to that vector of residuals, I can use the survey-weighted mean of those residuals distribution function to estimate the finite population CDF. Now, some details have been omitted here, but the idea is, instead of having the indicator function, I can replace the indicator function with its conditional expectation, conditioned on the set of covariates, with respect to the superpopulation model. As long as that estimate beta hat is consistent, which means that its sampling distribution becomes more tightly concentrated around the true parameters, then our CDF estimate will also be consistent for the finite population CDF. And lastly, once I obtain that estimate of the CDF, I can use a very generic quantile function to define its corresponding quantile estimator. Now, let us briefly discuss some results from simulations. So the idea of these Monte Carlo simulations essentially is to evaluate how well or how poor our proposed estimator works under a wide array of scenarios. So how we operationalize this idea of performance is by using the relative root mean squared error. And generically, the relative root mean squared error is just the ratio of the root mean squared error of an estimator divided by the root mean squared error of a gold standard. Now, since we want to estimate both the CDF and the quantile, we need to have two different gold standard estimators. Both of them are going to use Horvitz and Thompson's estimate of both the CDF and the corresponding quantile estimator. But the idea is that since we're using the relative root mean squared error, the estimator that performs the best should have the smallest relative root mean squared error. And when these values are close to 1, this tells us that our estimator is performing at a very similar rate compared to its respective gold standard. So now let's briefly talk about how we define the simulations. So for our finite population, we generated these finite population using 4 different superpopulation models. And these superpopulation models were defined such that we can observe the impact of model complexity on the performance of our estimator. For our probability sample, we just obtained a simple random sample without replacement of size 500 from each finite population. Now, for our convenience sample, I didn't mention this for a respective time, but it turns out that under some assumptions of specifically of ignorability, the estimate beta hat is a consistent estimate of the true parameters in the superpopulation model. However, we would like to see what happens when this assumption is violated. So we generated 2 different types of convenience samples, one for which the assumption of missing at random, or it's a flavor of ignorability, is satisfied, and the other for which this crucial assumption is violated. Again, we wanted to see what is the impact of violating this crucial assumption of ignorability on the performance of our estimators. And lastly, we were interested in estimation at the 1st, 10th, 25th, 50th, 75th, 90th, and 99th percentiles. So briefly giving an overview of the superpopulation models considered. If you take a look at model F1 and model F2, these are both quite simple models in that they only have 2 covariates. Again, we wanted to see what happens during simple models when we have a simple superpopulation model, and what happens when we gradually increase the complexity of the model. And so when we transition to model F3 and model F4, we can start to see that the model is becoming more and more complex and more nonlinear. So this is, again, the idea. We wanted to see what happens as we play with this assumption, this semi-parametric assumption. And last but not least, here are the estimators that we considered. For readability, I shortened the names to B, P, and R in the next slide, just so that we can kind of see the graph a little bit more, the relative root mean squared error values a little bit better. But essentially, we're calculating the naive CDF of B, which is just the empirical CDF using BY. We also considered a competitive plugin CDF estimator, where since we are missing the Y in the probability sample, we're substituting directly this missing Y with predictive values. And last but not least, we have our proposed residual ECDF estimator. Now, very briefly, taking a look at the relative root mean squared error values for both MAR missingness, which is missing at random or ignorability, and MNAR missingness, one thing that we want to note first is that the y-axis tells us the relative root mean squared errors. So again, we want to see a relative root mean squared error that's consistently the lowest, and preferably, we would like to see values that are close to 1. And I've highlighted 1 by this horizontal black line, this horizontal dotted black line. So one thing that we consistently see is using B by itself is not a good idea. The empirical CDF from B is almost always the most biased, whereas our residual ECDF estimator consistently performs the best overall, regardless of model complexity. But once we violate this assumption of missing at random, we still see the same pattern. The biggest difference that I want to emphasize on the slide is that the y-axis has increased dramatically. What this is telling us is that once we violate the crucial assumption of missing at random, our estimator, our residual ECDF estimator, will still perform the best overall, but we will see dramatic decreases in efficiency. And this is consistent with the literature. Now, to conclude, the biggest meat of this presentation was I wanted to see how we can extend the field of data integration to estimating cumulative distribution functions and their respective quantile functions. And the idea that I used was, instead of having this indicator function, let us substitute this indicator function with its conditional expectation with respect to the superpopulation model. And the idea is that if the semi-parametric assumption holds, that conditional expectation should be equal to the distribution function of the error terms with respect to the finite population at a specific fixed point. Now, the empirical results tell us that our residual ECDF estimator is quite robust to model misspecification if the missing at random assumption held, and it's robust to ignorability if the model was correctly specified. When both of these assumptions are violated, our proposed estimator will still perform the best overall, but we will again see noted decreases in efficiency. Our next steps is replacing the semi-parametric regression model with a non-parametric alternative. Specifically, I'm looking at using generalized additive models. So I know I'm a little bit over, so I wanted to turn the floor over for any questions or any comments. But I'm, again, so ecstatic to present this research, and I am so happy that you all are here to listen.
Thank you, Jeremy. I think we have time for just one question. Is there any questions?
Yeah, so I have a quick question about the function M.
Sure.
So far you assume the semi-parametric form. What kind of technical conditions do you need to do? Like, you assume it's known, it's semi-parametric. Other than that, what do you need?
We do need it we do need it to be continuous as well. But as long as it's known and it's continuous and it's parameterized by some vector of coefficients, those are the only 3 assumptions that we make with regards to that specific conditional expectation function.
So known in the sense that the covariate and the form should be known, right?
Yes.
Okay, I see.
But another assumption, a big assumption that we do need to make is the assumption of missing at random or ignorability. Because that is going to allow our estimates of the coefficients essentially to be consistent for the true parameters. But that is an assumption on the sampling design of B, the convenience sample.
Yeah, so that one is quite typical. All right. Yeah, thank you. Yeah, thanks.
Thank you.
Thank you, Jeremy. For the second speaker, we have Thomas Johnson from North Carolina Agricultural and Technical State University. Please welcome Thomas Johnson. Oh, he'll be talking about the impact of data perturbation for statistical disclosure control on the predictive performance of machine learning techniques.
Thank you. Can everybody hear me?
Yep.
Yep, thank you. And thank you everyone for this opportunity to present this research. So basically my research deals with the usage of statistical disclosure control methods for this presentation, and I'll be getting into that very shortly. So as we all know, that data is critical to research, is basically going into big data, huge volumes of it, high throughput, and additionally, there are various types of data, various contexts in which data is utilized. And in some cases, we have variables within the data that are sensitive or have vulnerable information that in the original form of that data, we can't necessarily distribute it out to the broader research community or use it in our typical workflows because that could endanger the privacy of the participants in that data. And so essentially what comes about is statistical disclosure control. So the assortment of methods, processes, and procedures in order to better allow for our data to be distributed and utilized without endangering that privacy or to ensure a certain grade of privacy protection. And so general motivations can be seen in healthcare information, as well as with financial information, such as if you're collecting income data on various individuals. Naturally, people can be very reluctant to provide that information or feel very insecure that that information is being held anywhere because that can be utilized to identify that specific person. And likewise, that can in turn be utilized to, say, violate certain rights or protections that person has or securities that person would seek out. And so in our objective, what we're doing is exploring two SDC methods for continuous data specifically, the GADP method or general additive data perturbation and the CGADP method, copula general additive data perturbation using the Gaussian copula. And so you might be asking, what is GADP? So the main thing to take away from this slide is we have two matrices, matrix A and matrix B. Matrix A contains publicly available or non-vulnerable information, and matrix B contains the vulnerable or sensitive information that in turn we need to do perturbation on in order to be able to release to a broader research community or utilize in our workflows because of that vulnerable information. So ultimately what it comes down to is we have an assumption that the variables within A and B are normally distributed, and we consider the entire data matrix of A and B combined together as matrix C. And throughout the GAD process, basically what we're doing is we're taking the statistical information of mu A, mu B, denoting the mean vectors of A and B, as well as sigma A, sigma B, denoting the variance covariance matrices of A and B. And we're also getting the mu and sigma with relation to C. And then key point here on this slide is that we introduce a privacy protection parameter called theta. And what theta essentially allows us to do is determine the amount of data utility versus privacy trade-off that we want to use. And so if we want to maximize our privacy protection for the individuals in the data set, that naturally comes at the expense of data utility. And if we want more data utility, that naturally comes at the expense of the privacy protection. And the whole idea is that utilizing the previous information, what we're going to do is we're going to generate matrix D using the properties of the multivariate normal distribution and use the conditional distribution utilizing the information in C, A, and B, so that we get matrix D, which has perturbed data that we can then utilize within our workflows. And so this is just a more general graphical description of what's happening. And so we can see in step one, we're basically accumulating the information with respect to the variance and covariance and the mean vectors. Then in step two, what we're basically doing is we're getting the statistical information as it relates to matrix D. Then as we go into further down in step two, we start generating the necessary statistical information for each random variate of D. And as you can see, for the mean vector of D, it's basically the mean vector for that specific individual in the matrix D as it relates to the specific individual in matrix C. And then we just have a general variance covariance matrix for sigma D that takes into account that that privacy protection parameter that we square and multiply into the variance covariance of matrix B. And then finally, we generate the matrix D from the information that we previously collected in step 2. And for step 4 is just utilizing the matrix D and A for our workflows or analysis versus using matrices A and B. So for CGADP, it is an extension of GADP that basically takes into account that having the data be normally distributed is a strong assumption, as we know that data can take on multiple forms and multiple variables can belong to varying distributions. So what happens is we utilize copulas in order to take advantage of the Gaussian copula and essentially use the CDF and inverse CDF functions in order to convert our variables all to the normal distribution and then proceed to utilize the GADP method. And what this allows is for us to utilize the GADP method without worrying so much about the violations that can be incurred from utilizing varying distributions, such as a variable having a binomial distribution or a variable having a gamma distribution, so on and so forth, that may violate the normality. And so as some initial pre-processing steps, once we're utilizing that inverse CDF and CDF function to do our transformations, we also have to compute the Spearman correlation matrix. And in turn, we can then use the Pearson correlation matrix. And then from there, we can utilize that to basically carry on the same steps. And a last step in the procedure is that for D tilde, we basically utilize the inverse CDF and CDF functions in order to convert matrix D tilde back into the distributions that would be expected for matrix D based on matrix B. And so to look at the machine learning techniques we were evaluating, we of course started off with linear regression, lasso, then neural network. We had 3 varying SVMs by the kernel that was used, random forest, XG boosted trees, and then stacked ensembles, one with equal weighting. So each of the previous linear regression to XG boosted tree models were given equal weighting. And then for the stacked ensemble with proportional weighting, those previous machine learning models were in turn given weight inverse to their training MSE. So if the model did better in the training step, that in turn allowed it to contribute more in the stacked ensemble with proportional weighting. So we had various simulation models. Specifically, we were focusing on the usage of the multivariate context. And so for each model, essentially 2 sensitive variables were generated that differed by the noise level. We also wanted to, and the reason for that is we also wanted to see how the varying the noise would in turn affect the GADP, CGADP processes, and in turn the machine learning's models prediction performance. And as you can see here, we generate a linear model as well as a second model that is nonlinear that has various jumps for the response. And so for our simulation settings, we had 1,000 Monte Carlo simulations for each combination of parameters for our simulation models. And included amongst these parameters is the privacy parameter that was utilized. So we have levels 0.2 to 0.8. 0.8 meaning high data utility, 0.2 meaning high privacy preservation. And we had a maximum of 10 predictors for each model, and any predictors that weren't included as significant or actually contributing were just considered noise. And for the training size, we varied those as well. And for the testing set, one fixed testing set was generated for all our for each combination of parameters, so that we can see how after doing GADP or CGADP and applying these models, one lasso that was trained on the perturbed data set, one lasso that was trained on the non-perturbed data set, how those differ. So we measured the mean squared prediction error and also calculated the relative MSE in order to see how the perturbation affected the machine learning algorithm's performance and prediction. And so just under model 1 with GADP, the neural network and the stacked ensemble with equal weighting performed terribly, and we had to remove those from the graph in order to see the rest. But as we can see, the MSER for a good multitude of the models is holding steadily at lower values, but we can see that there are definitely issues with the stacked ensemble with proportional weighting and the XGB tree. Shifting over to CGADP, we can see that it's shifted so that the stacked ensemble with equal weighting was able to be re-included, but we can still see that it has varying performance issues. When we go to model 2 with GADP, likewise, we can see that we had to exclude the XGB tree and stacked ensemble with proportional weighting due to poor performance. But we can see that the random forest and the neural network are definitely suffering under this perturbation method. And likewise, under CGADP, we can still see the same pattern with the random forest and neural networks suffering under under the CGADP method. And so for a general summary table of model 1, we can see that generally the model with the best MSE under GADP was linear regression. And also the model with the best MSER was linear regression. And since it's so close to 1, we can see the GADP didn't really affect this prediction performance. Under CGADP, we start to see that the polynomial SVM takes the best in terms of MSER, and these varying levels of the MSER show that under CGADP, various models were beginning to become affected by the perturbation method. For model 2 under GADP, we see that the best MSE under GADP was typically held by lasso with some linear SVM and random forest interventions. And then in terms of the best MSER, that was typically held by the linear SVM. Now moving on to CGADP, we can see that typically the linear regression was taking point when it came to the best MSE and MSER, when it came to the rho equals 0.2 and rho equals 0.4 cases. But once we get to rho equals 0.6, lasso and random forest were typically trading off. And so just in a general summary, we could ultimately see that under GADP, lasso, linear regression, and linear SVM were usually the ones that had the lowest MSER across each of the scenarios. And in terms of model 1 under CGADP, we saw that the polynomial SVM had the lowest MSER. And part of that is because the MSE for both the perturbed case and non-perturbed case were so close that ultimately it was highly unaffected, or the other models just had such a widening gap due in the perturbed case and non-perturbed case. And additionally, we can ultimately see that it's a good thing to include the best MSE because the MSER can be somewhat misleading, as a machine learning model could perform badly in both the perturbed case and a non-perturbed case, and as a result have a low MSER, but its MSE could be wildly different from the other models and a negative point. I would just like to say thanks to my advisor, thanks to all of you for this opportunity, and thanks to Jeremy, my research colleague and the research team, and Title III. And here's my works cited, and I would like to take any questions that we have.
Yeah, we have time for 1 or 2 questions. Okay. Thank you, Thomas, for presentation.
Thank you for the opportunity.
Next. Yeah. So next we have Yikun Zhang, a PhD student from University of Washington. So Yikun Zhang will be presenting his work on efficient inference on high-dimensional linear models with missing outcomes.
Okay, so first of all, can anyone hear me on Zoom?
Yeah, but your audio isn't that great, to be honest.
Oh yes, can you hear me right now?
Yeah, I
Or-
can hear you.
Okay, so yeah, thank you all for joining today's conference. And first of all, I would like to thank the NISS for organizing such a wonderful graduate students network research conference. And today is also my great pleasure to share my recent work on efficient inference on the high-dimensional linear model with missing outcome. And this is Zhang Wang with Alexander Disney and my advisor Yan-Qi Chen. And I would like to give you some short motivation of why we want to study this high-dimensional inference problem. So we all know that nowadays we always encounter some high-dimensional data in practice, especially when the numbers of covariate is much larger than the sample size. And also in the observational study, there are also we encounter some cases where some outcome variable would potentially be missing. And one concrete application in our mind is in astronomy, where we want to conduct some value inference on the stellar mass of the observed galaxy by the Sloan Digital Sky Surveys. And in particular, SDSS will record millions of galaxies together with their spectroscopic and the photometric properties. However, some of these stellar mass could be missing in the associated value-added catalog published by the SDSS. And if we focus on the high redshift side, for instance, from the 0.4 to the 0.401, we will see that in the plot here that around 30% of the galaxy whose stellar mass are indeed missing. And the reasons why this is a high-dimensional inference problem is because we always want to generate some nonlinear features in order to capture those complex patterns in the observed galaxy data. And we also want to apply the parametric model in order to maintain the interpretability of our inference. And also the reasons why we'll encounter those missingness in the stellar mass is because there will be some limited usage of the observational run in the Sloan Digital Sky Surveys for the galaxy target. And also there could be some potential data contamination when we observe those galaxies. And in some cases, those galaxies could be misspecified as the stars. All of this we introduce the missingness in the estimated stellar mass of those observed galaxies. And because of this, and the scientific question that we want to answer on this data set is that how we can conduct the value inference on the stellar mass of a newly observed galaxy based on its spectroscopic and the photometric properties. And in order to answer this scientific question, we would like to first translate it in a statistical language. Or equivalently, to interpret it in a statistical language, this basically say that we want to solve a high-dimensional inference problem with the missing outcomes. And there are two different challenges like we see in this problem. The first is the high dimensionality of the data, and the second is that there will be some missingness inside the outcome function. And in order to solve in order to reconcile the high dimensionality inside the data, we assume that the observational data that we have is come from a sparse linear model, where the coefficient here will have the numbers of non-zero entrants, which is much smaller than the dimension d, and the R is indicating whether the observed variable is missing or not. And these linearity assumptions it can be relaxed to use to the sparse additive model, partial linear model, or even the weakly sparse linear model. And our proposed methodology and the theory that we'll show you in a second would be easily adapted to all these general cases. In order to handle the missingness in the outcome, we will assume the outcome is missing at random, basically saying that the outcome variable will be independent of the missingness index given the high dimensional covariance. And this assumption is particularly weak in the context of high-dimensional inference is because we can always incorporate as many covariates as possible in order to control for this confounding effect. There are already some existing work that has been done on this high-dimensional inference problem, but most of this existing work focus on the statistical inference on this high-dimensional regression coefficient. So when the outcome is fully observed, when there are no mismatches in the outcome, the famous debiased lasso has been proposed before. And basically what this debiased lasso approach did is to first feed a lasso pilot estimate on the data, and then you have an additive term that correct the bias that produced by the lasso solution. And within this bias correction term, there will be an approximation of the inverse of the Gram matrix. And also, when the outcome is missing at random, there is also an M estimation framework that has been proposed together with the lasso type debias and double robust estimator. However, there are some existing drawbacks of this approach. First, computationally, you always need to compute this D by D debiasing matrix, which is an approximation of the inverse of the Gram matrix. And when the dimension D is high, this will always incur some computational issue. And for the M-specific framework specifically, you will always require the sample fitting and cross fitting in order for their estimator to be valid. And in order to reconcile this computational issue and the loss of the statistical efficiency, we propose instead to focus the inference on the linear regression function. And there will be low loss of the generality by focusing on this linear regression function is because we can always choose the query point X such that we can do the inference on some specific coordinate of the regression coefficient or the linear combination of this regression coefficients. And more importantly, our proposed debiased estimator would be both computationally and statistically efficient. From the computation perspective, our Cornell debiasing program would be convex, and we only need to solve for an n-dimensional wave vector instead of a D by D debiasing matrix. Statistically, our estimator will be semi-parametric efficient among all the asymptotic linear estimator. And now let me walk you through the proposed methodology that we have. And recall that from the debiased lasso, we are always correcting the bias of the lasso pilot estimate with a bias correction term here. And one naive debiased estimator people might think about is that we can just multiply the X transpose to the debiased lasso solution in order to get a debiased estimator for the linear regression function. However, there are two issues of this naive debiased estimator. The first one, as I mentioned earlier, we always need to estimate a D by D debiased matrix which will be computationally expensive when the dimension D is high. And more importantly, this naive estimator might not be asymptotically normal in general, especially when the query point is not sparse. In order to reconcile this, in order to reconcile the previous issue, we will notice that there is this X transpose theta hat and xi here. Basically, it's just a scalar, and we can always replace this scalar by some weight in this summation. And by doing this, we can introduce a generic debiased estimator which will only involve a wave vector with n dimension. And now the question becomes how we can estimate this wave vector from the data using some efficient approach. In order to estimate this way, we will look at the conditional mean square error of this scale debiased estimator. So it turns out that the conditional mean square error of this debiased estimator can be decomposed into three different terms. The first term is the conditional variance term, and the second term is the conditional bias term, while the third term also comes from the conditional variance, but you will be asymptotically negligible. And if we know the asymptotically negligible term, these conditional bias would becomes the traditional bias and variance trade-off scenario. And in order to control for the bias, we can always apply the Holder inequality to get an upper bound of this bias. Then our proposed debiasing program would be to minimizing the estimated conditional variance as an objective function and subject to the constraint where the upper bound of this bias would be well controlled. Now, let me walk you through the entire debiasing inference procedure that we propose. We will, similar to the debiased lasso approach, we will also start with computing a lasso pilot estimate on the complete case data. Then we will estimate the propensity score using any machine learning methods. And I will show you later why we can actually estimate the propensity score using any non-parametrically without worrying about the issue of overfitting. And third, we will solve our previous debiasing program, which will optimally trade off between the bias and the variance. And after we obtain the weight from the debiased program, we will plug in the weight into the generic debiased estimator to get our final debiased estimator for conducting the valid inference on the linear regression function. But by using our debiasing inference framework, there are still two unanswered questions that we haven't solved. First, the first question is, how can we select the tuning parameter in our debiasing program? The second question is, would our final debiased estimator be asymptotically normal? And interestingly, both of these questions can be answered by the dual formulation of our debiasing program. So recall that this is our primal debiasing program, which is a quadratic programming problem with L infinity constraint. And if we do work out some algebra, we can show that the dual formulation of our debiasing program will take the form like this, which is again a quadratic programming problem, but it becomes an unconstrained optimization problem. And more importantly, under the strong duality, we can always connect the primal and dual solution using the equation as I show here. And this will become very helpful for us in both the theory and practice. So practically, because the dual program is an unconstrained optimization problem, so the tuning parameter gamma here can always be fine-tuned using the cost validation on the data. And theoretically, these primal and dual relations can actually tell us how to establish the asymptotic normality of our estimator. So by plugging in these dual primal relations into our debiased estimator, and we can show that under some regularity condition, the dual solution will converge to some quantity that's independent of the data, and then the first term here will become the sample average of the IID random variables. Because of this, we can apply the classical central limit theorem to divide the asymptotic normality of our debiased estimator. And given the heuristic that I showed in the previous slide, we will have the main theorems of this work is to prove the asymptotic normality of the debiased estimator. And one interesting remark that I want to make here is that the asymptotic variance of our debiased estimator is indeed attains the semi-parametric efficiency bound among all the asymptotic linear estimator under the Meson random outcome. And this actually show the statistical benefits of using our debiased estimator to conduct the inference on the regression function. And also, in practice, under some regularity condition, this asymptotic variance can also be consistently estimated by the objective function of our debiased program. Now, I want to share with you some extra insights about why we don't in the propensity score estimations. So if you go to the statistical conference nowadays, you always see that the sample splitting and the cross fitting is always required for the debiased inference if we want to use the machine learning approach to estimate the nuisance function. In our case, the nuisance function is the propensity score, but the interesting question is, why don't we need the sample splitting or the cross fitting for estimating the propensity score, even when we are estimating using the machine learning approach? And the answer is, our asymptotic normality results is only depends on the in-sample estimation error of the percentage score. And in other words, our device estimator will perform even better when we overfit the percentage scores. And this phenomenon is more or less coincides with the benign overfitting in the linear regressions or even the neural network setting. And now I would like to quickly show you some simulation results, and then I will go back to revisit our previous applications on the stellar mass inference. So this is a quick summary of the simulation results. So basically, if we only use lasso pilot estimate to conduct the inference, we always get some bias estimate, and our device estimator can be effectively correct the bias of the lasso pilot estimate. And more importantly, we don't have to use any sample splitting and the cross-fitting, and the propensity score can be fit using the same data. And more importantly, our device's estimator will be asymptotically normal under a wide range choice of the tuning parameter gamma. And now I want to go back to the motivations of our study, that we want to conduct the value inference of the stellar mass of the observed galaxy in astronomy. So as a small recap, the scientific question that we want to ask is how we can conduct the value inference on the estimated stellar mass based on its spectroscopic and the photometric properties. Another more interesting question is it statistically significant that the stellar mass of the galaxy is actually negatively correlated with its distance to the nearby cosmic filament structure that has been shown in the literature in astronomy. And here is the results that I show that apply our device estimator to conduct the inference. On the left panel, you can see that our device methods, different from the traditional approach, you can always cover the true stellar mass of the newly observed galaxy. And on the right panel, the 95% confidence interval of our device method is also excluding a 0, and it will show the negative trend. And it actually tells us that these negative relations between the galaxy stellar mass and also its distance to the nearby cosmic filament is indeed statistically significant. So now I will want to quickly give you a summary of my today's talk. So in this talk, we actually show you efficient devising approach for conducting value inference on the high-dimensional linear model, even when the outcome is missing at random. And in particular, our device estimator will be both computationally and statistically efficient. And all this efficiency can be explained through the dual formulation of our devising program. And more importantly, the nuisance parameters, the propensity score, can be non-parametrically estimated without any sample splitting and cross-fitting, and we can use any machine learning method that you want. And we also show you a novel application to the inference of the stellar mass of the observed galaxy by the Stone Digital Sky Survey. And more details of our work can be found in the paper, and we also publish both the Python and R package for our device methods. And with this, I would like to thank you for your attention, and I'm happy to take more questions.
Thank you. I think we already have 2 questions. Maybe can you look at the chat and answer some of them in next couple minutes?
Sure. So, so the first question is, were other variants of the lasso considered the pilot estimates, such as adaptive lasso or relaxed lasso? Yeah, that's a really good question. So, actually, for other variants of lasso, you can also use our framework to conduct value inference, because we all know that like the original lasso solution will actually give a bias estimate. So as I showed in the previous slides, but for both adaptive lasso and relaxed lasso, they will also be biased, and we can always plug in these like the adaptive lasso solution or the relaxed lasso solutions to our framework to conduct the value inference. And the second question is, has ElastiLab been suggested as the pilot estimate? We haven't tried the ElastiLab, but we believe that it can also be used to conduct the value inference into our framework. So, and this will be an interesting future work that we will keep that in mind. Yeah, thank you for the question.
Thank you. For the interest of time, let's move on to our next speaker. We have Yi Liu, a PhD student from North Carolina State University. Yi will be presenting on multi-source conformal inference under distribution shifts.
Yeah, thank you. Can you hear me?
Yep.
Okay, so thank you for the letting me to present my work here. So let me share my screen. Yeah, can you see this screen well?
Yep.
Okay, yeah, thank you so much. So so today I'm going to present our very recent work about multi-source conformal inference under distribution shift. So this is a joint work with these great people. I want to give a big acknowledgement to them. And they formalized and conceptualized this idea very earlier, and we are really motivated by a practically important issue. So our first, I will give an introduction to a motivating example of this work. So we are motivated by the issue on the congenital heart defects, the CHD. That is the most common birth defects in the United States. And we have a large data source, the STS-CHD database, and we'll focus on the novel surgeries data. Those surgeries performed from 2016 to 2022. Our primary outcome interest is the post-surgery length of stay, the LOS in hospital. This outcome will have some very important practical meaning, such as if you prolong the length of stay, you will create some financial burden to families and our healthcare system. So it's very useful to know some information about the LOS. So in this data, we have 3,000 more observations, but some of them are missing values in the outcome. So this motivates us to think about the prediction of these missing values. So we have like about 20% missing LOS value in this data, as you can see. Our goal in this project is for a new patient who arrives at the hospital, can we provide a prediction interval that will contain the true length of stay with some pre-specified coverage level 1 minus alpha? So yeah, maybe a little weird today. I want to first share some data analysis result before moving to method, because I want to let you have a sense about how the this method under the framework will be result will be looking like. So as you can see, we can by applying our method and some other computing methods, we can plot the prediction interval at different coverage level. This is a miscoverage level alpha. By choosing different conformal scores, this will be introduced later. But you can see the prediction interval sometimes by some methods are wider, by some methods are shorter. The red one is our proposed method. It can be shorter and by another method, or sometimes it can be a little bit wider. But later we will see the two other methods can be biased. So let's first have some background checking on the conformal inference. That is a theoretical foundation of our work today. So suppose we have some IAD training samples, Xi and Yi. Xi are the covariate of our predictors and Yi the outcome interest. And we have a testing point that is outcome is unknown, but we have the predictor and they assume from the same distribution of the sample. So conformal inference aims to construct a prediction interval C hat given the predictors with this coverage guaranteeing that is the outcome belongs to the prediction interval should have the 1 minus alpha coverage level. So this is the the unique feature of the conformal inference distinguished from the traditional statistical inference is that we want the prediction interval to be valid in finite samples for any distribution and any predictive algorithm. So the conformal here can be understood like it should be inclusive to different model. So it's unlike the traditional statistics. We have the we need to derive asymptotic normal distribution and make the inference under a specific distribution. And in addition, we also try to want the efficient prediction interval, that is to minimize the weights of the prediction interval. But today, so we will work on a little bit different question, but it's under the conformal inference framework. That is, we obtain valid distribution-free prediction interval for missing outcomes in a target population while we're leveraging multiple other potentially biased source populations. So by doing this, we further introduce some notation. Suppose we have data from k different sites, and for each site, we observe a covariate vector x, and then we use the capital T to denote the study sites in the data, where the 0, T equals 0 indicates the target site, and the rest k-1 sites are other source sites. Source sites can be biased again. So we also use the R as indicator of the missing, the observing outcome. That is R equals 1 if the Y is observed. So by doing this, by having this indicator, we can have our data, observed data in the format. It's IID copies of the covariate, site indicator, missingness indicator, and the observed outcome. So this is essentially a missing data program. And so we have the working assumptions that are very standard in the missing data literature, the missing at random, and also the positivity assumption. Starting from a single site, okay, so our goal is to construct the prediction intervals, say hat alpha of x, such that this equation, this inequality holds. This means the prediction tailored for missing outcomes r equals 0 in the target site, the t equals 0 here. This prediction should have the guarantee of the marginal coverage 1 minus alpha. In conformal inference, the way of doing this is to introduce a so-called conformal score, the function of x and y. The prediction will be based on the conformal score. The prediction set will be look like for all y, such as the conformal score, given a fixed x should less than equal to threshold of the conformal score. The estimated thresholds, and this r hat here, r hat is the estimate of the R0 is the true 1 minus alpha quantile of the conformal score S in the target site. And the R0 is identifiable under the missing at random assumption through an estimating equation. So by the estimating equation theory, you probably know that each parameter, such as the parameter here R0, they can have a lot of different estimating equations, right? But among those estimating equations, there can be one such as the resulted estimates is the most efficient and robust estimate of the parameter. So there is a very exciting work very recently by these authors, Zhang et al. They proposed an efficient estimator of the functional 1 minus alpha quantile conformal score on by this efficient nonparametric efficient inference function. So this efficient inference function is given in this format, where these have two nonsense function in the estimating equation. One is the M0, which is the assumed CDF of the conformal score. The other one is eta 0, which is a missingness risk ratio. So when using this the efficient inference function, right? So you can solve the estimates R0 hat from the estimation equation based on this efficient inference function. That is the empirical, solving the empirical average of the inference function by plugging some estimate of the Newton function and setting this equation to 0. So you can get an estimator R0 hat of the interesting parameter. And this is a robust estimator and efficient estimator. However, applying their methods in our diagram, we only get the data. We only that will be using only data from the target site itself. But now we consider we have multi-source data. So to leverage data from other sites, we consider two cases of the homogeneity. The homogeneity is for the conditional outcome distribution across sites, right? Because different sites can be potentially biased, so their conditional outcome are not necessary to be the same. But we consider this case separately to make the theory achieve the best of our knowledge to be the best. So if this homogeneity holds, we propose a fully efficient estimator. If it does not hold, we propose a data adaptive strategy to upweight those informative sources while downweight those non-informative sources. So the first case is when that homogeneity holds. So we call that efficient prediction under common conditional outcome distribution, the CCOD. So we also following the very similar technique used in theorem 1. We also derive the efficient inference function under CCOD for the R0, the quantile. So they have here the format is almost the same for the theorem one, but it's a little bit different when we have multiple data sources. So there are some different Nielsen function, the M bar, eta bar, and the Q0. The M bar is a global CDF of the conformal score, while the eta bar is the global missiness ratio, which means they do not depend on the site variable. But there is additional Nielsen function, the Q0, which is a target site propensity. So this CCOD estimator, we can show that they have fast convergence rates, which is essentially the parameter rates, and it also supports flexible estimator for this Nielsen function. Once they are estimated well, the nominal coverage guarantee is achieved by this CCOD estimator. However, in practice, it will often be unreasonable to assume the conditional outcome distribution is the same across sites. So because it's really, in this case, it will be very challenging to develop such a simple and efficient estimator. So the way we do this is to combine using a data adaptive manner to combine information. So first, the theorem 3, we introduce the efficient estimation of R0 using the source site K. So note that here, by using the source site K, we want to use the source site K to estimate the conformal score of the target sites. So this inference function will not be the inference function as theorem 1 using a source site K data, but we have some projection from the source site K to the target site. So the inference function is looked at like this way, where we have 3 Nielsen function, the M0, the CDF of the conformal score in the target site, MK, the CDF of conformal score in the site K, and also a density ratio. This plays a role of projecting the information from source site to the target site. So we can similarly solve the estimating equation in this source site, but by this construction, the quantile will use the data from both site K and the target site. But actually, we using some similar logic in this paper, we show that we only need to pass some summary statistics. So there is also satisfy some data sharing privacy constraint. The next step is for data adaptive aggregation. So after we have the estimates of the parameter from different sites, we first compute the discrimination measures chi-square, that is a conformal score estimation from the target site and the minus the conformal score of the estimator from the source site. The square difference of this discrimination measure. So next we solve the optimization paradigm using this adaptive Lafso type of the penalization and minimization procedure, get a data adaptive weights, and then we aggregate all of these estimators in our in this weighted sum format. Sorry, and then the prediction interval will be defined as using the weighted average of the conformal score across different sites. So this is an algorithm diagram of our proposed method. So you see we have solving different conformal score from different sites and then aggregate them together. So finally, let me introduce our numerical experiments of the proposed method. We consider different sites, sample sites, and then we consider different levels of covariate shift and outcome errors. So in total, the detail can be found in our paper, and in total we have 100 more scenarios in our numerical experiment. And then in this page, we show some results, and I will just comment the panel A. For other panels, you can find the details in our paper as well. So the red box one is our proposed method. As we can see, this one, this red dotted line is a benchmark of the coverage probability. Our methods always close to the nominal coverage level, and some other method can be biased. And the third method, the blue one here, has a little bit wider box than our method, so it's less efficient. So let me give a wrap up for today's discussion. So we proposed a method that obtain valid prediction intervals for missing outcome using multi-source data. Some of the source data can be potentially biased. And we have marginal coverage probability guaranteed under some strong assumptions, but we also show in our simulation study, our methods also works very well under the heterogeneous outcome distribution. So a final remark is about some future research. So I would like to see the conformal inference has a very promising future. Some other aspects we can consider is, for example, the weights can be more efficient using correlated adaptive ensemble weight for aggregating information, which will targeting to achieve the oracle efficiency. We also want to consider the issue, the more strong guaranteeing, that is a conditional coverage guaranteeing. So to construct the personalized conformal prediction interval. And there are some interesting attention to causal inference literature and also the issues of violation of the positivity and missing at random assumptions. Finally, very excited that the paper is accepted at the International Conference of the Machine Learning 2024. So feel free to scan this QR code for the full version of the paper and reach out to me at my email and with more information at my website. So thanks everyone. It's a very good experience to presenting our work. So I will answer any questions you have now.
Yeah, we have 4 minutes for a couple of questions.
Hi, yes, thank you for a great talk. So one question that I have is the last bullet point that you showed in the last slide. So basically you said it can be extended to like the violation of the positive assumption. So would you elaborate more about how you're going to resolve this, like the violation of the positivity assumption in this conformal inference context?
Yeah, thank you. This is a very great question. So actually, unfortunately, we haven't thought about this into details a lot. But the truth is that in some cases, you have not very large missingness proportion in your data. So in practice, some people for doing this is like that. Okay, if the missingness proportion in your data is not that large enough to satisfy the positivity assumption, they may also like manually make some other part of the data to be missing, so that they create some like pseudo missingness pattern of the data. Then they make the data satisfy the assumptions. So yeah, in the future, we would like to probably consider like some techniques used in the so like the truncation or propagandistical trimming techniques similarly used in the propagandistical weighting literature for tackle this issue. But so far we haven't thought a lot of details on this. But in practice, there is some real data challenging that if your data has very smaller amount of the missingness ratio, then the missing data prediction can be challenging using this method. Yeah. That is how we were thinking about this, why we present the violation of the positivity assumption as a challenging here. Yeah.
Thank you. Thank you for the answer.
Thank you.
I think we have time for one more question. All right, if not, thank you, I think that concludes our second session.